Hi guys, so I'm going to start a series about how to control the SO101 6 degree of freedom arm. The SO101 6 degree of freedom arm is a modified version of the open source SO101 arm which has 5 degrees of freedom. We at Rockford Robotics have added an additional degree of freedom to make the arm more dexterous and more capable of performing better tasks. I am planning to start a series explaining the different aspects of how to control the arm, the math behind the robotics, and how to use AI to make the robot intelligent and perform intelligent tasks. In this first video, I am going to start with forward kinematics. Forward kinematics is fundamental to how an arm works, so I figured it would be a nice starting point. I have prepared a bunch of slides and videos to explain how the arm works. To start with, let's look at a 3D visualization of the arm. So here we have a 3D visualization of the arm along with different sliders here that controls the angles of different joints. In the real arm, these joint angles will be controlled by servo motors. So first is the shoulder pan joint, next is the shoulder lift joint, next we have the elbow lift joint, elbow rotation joint, which is the joint which we added in addition to the original SO101 arm. Next we have the wrist flex joint, wrist roll joint, and this is for the gripper. So we have 1, 2, 3, 4, 5, 6 motors. That's why this is a 6 degree of freedom arm. The gripper is for grabbing items and that doesn't count as part of the degree of freedom traditionally. So what is forward kinematics? Forward kinematics is the way to figure out where the end effector, which is denoted by this red dot, or the tool will go to in the 3D space given different values for the different arm joints. So for example, I move this joint, the end effector moves. I can move this joint to move the end effector, and I can move any of these joints to move the end effector. And forward kinematics is the math that explains where the end effector will be for a given set of joint values. So these are the things we are going to learn about in this video. What is forward kinematics and why it matters? Define the problem in more mathematical terms. Post that, we will start deriving mathematically the forward kinematics equations for the arm. We will start with a one link arm with one joint, then move to 2 joints, then to 3. This will give us deep intuition of what forward kinematics is. Next, we will transition to matrices. Why do we need matrices? Matrices simplify a lot and computers work very well with matrices. We'll look at coordinate frames and coordinate transformations, 3D rotation matrices, homogeneous transformations, which combine both rotation and translation. With all these details, we will look at how to exactly derive the forward kinematics equations for the 6D of SO101 arm. And finally, we will look at some pseudo code and Python code to how to implement forward kinematics. So what is forward kinematics? Forward kinematics is simple but a crucial one. It tells us for a given set of joint angles where exactly the robot's hand or end effector lies. So these are the different joint angles, and given these joint angles, we need to find out where exactly the XYZ position of the end effector will lie. So as I mentioned before, each of the joint angle values in the physical arm will be controlled by a servo motor. We can set different positions for the servo motor, and the servo motor can precisely move to that position. So why is forward kinematics important? Forward kinematics is used for motion planning, collision detection, and as a fundamental part of inverse kinematics. All these are fundamental to how the robot arm works, and we need to understand these to make the robot arm perform tasks in the real world. In the upcoming videos, we will look at each of these in more detail. So in more mathematical terms, we can look at forward kinematics as a function that maps joint space to Cartesian space. So given these theta angles of the joints, we compute a function that returns the xyz coordinates of the end effector along with the rotation matrix of the end effector, which gives the orientation of the end effector. We will look at this in more detail in the upcoming slides, but basically this function f is what we are going to compute, which is the forward kinematics of the arm. Okay, now we will start talking about forward kinematics of a simple one link arm. This will help us build intuition to how to derive it for more complex arms. So here we have a one link arm defined by one joint theta. L is the length of the link. We can adjust the joint angle value theta and also the link length. We can see that the end effector's xy coordinate changes as we change the angle theta. So with basic trigonometry, let's look at how to derive the equations for the end effector's coordinates. Okay, this is the derivation. This uses simple trigonometry to arrive at the equations. So we assume the length of the link is L and theta is the joint angle. So we know that sin theta is opposite by hypotenuse and cos theta is adjacent by hypotenuse using basic trigonometry. By multiplying both sides by L, we get x as L cos theta and y as L sin theta. For people who understand coordinate geometry a bit more, this would be even easier to understand, because this end effector point traces a circle, and these equations are precisely the parametric equations of a circle with radius L. Now let's add a bit more complexity. Instead of just having one link, let's have two links. So here we have two links and two joint angles, theta 1, one for the elbow, and theta 1 for the shoulder, and theta 2 for the elbow. We can see that we can control both angles here, and the end effector point moves based on that. Okay, so how do we derive the equations for this arm? Let's first derive the equation for the elbow joint. As you can see, controlling the shoulder's angle moves the elbow joint, which is this point, and this precisely has the same equation for the one link arm which we saw previously, because the same, we have a length, we have a theta, and the same trigonometry equations give x1 and y1. Okay, based on this, how do we get the next link's position? This is the critical insight here. This angle theta 2 for the second link is relative to the first link L1, but to compute the total angle from the x-axis we have to add both the joint angles theta 1 and theta 2. So now we do the same thing again from this point. For this right angle triangle, instead of the angle being theta 1, the angle will be theta 1 plus theta 2, and instead of the length being L1, the length is L2. So from this point, if we consider this as the starting point, and if we compute the coordinates of this end point, it will be L2 cos theta 1 plus theta 2 and L2 sin theta 1 plus theta 2. But since we need the points relative to this point, not instead of this point, first we have to add this point, then we have to add the relative distances from this point. So we get x equal to x1 plus the second relative distance. Similarly for y, and since we already have figured out the elbows position x1 and y1, we can substitute that here to get the final equations. So we now know how to compute the forward kinematics for a two-link arm that operates in a plane. Actually, for a arm that operates in a plane, this pattern continues. Say we had a third link and that link also operates in the same plane, we can just add plus L3 cos theta 1 plus theta 2 plus theta 3, and similarly for y we can add plus L3 plus sin theta 1 plus theta 2 plus theta 3, and so on for any number of angles. Now let's do three-link arm, but this time in 3D. So far we have seen only all the joints operating in the same plane. Now let's look at a 3D example. Now we have three angles, theta 1 which rotates the arm out of the plane, theta 2 and theta 3 which rotate the arm along a plane. So we can use the previous derivation to compute the changes given by theta 2 and theta 3. For a fixed angle, say let's fix it at 0, if this theta 1 is not present, this theta 2 and theta 3 act very similar to the previous example with just two thetas, because these two thetas are in the same plane. So if we consider this distance as r, we can use the same equations as we did for the previous arm. So here we can see this is the distance r if you look at a side view of the arm. So this r is the x distance which we calculated previously for the two-link arm example. And if we consider this distance as z, this is similar to the y value of the previous example, but with an additional L1 added to it because of this height, because here the starting point itself has been shifted by L1. So here we get z as L1 plus the similar equation as we derived previously, and for the r we get the x-axis equation we derived previously. But we don't just need r, we need x and y. So if you look at a top view of the arm, we see this diagram. So this is the r, and we can resolve this r based on this angle theta 1 as r sin theta and this x as r cos theta. So substituting these values we get this. So C2 is cos theta 2, C23 is cos theta 2 plus theta 3. So for r we substitute this r's equation, then multiply it with cos theta 1. Similarly for y we substitute r's equation, but this time multiply it by sin theta 1. So we have successfully derived the forward kinematics for a 3-joint arm in 3 dimensions. Just to recap quickly, we have these two angles which act very similar to the previous 2-link arm derivation, and this the distance, x distance of this two angles is given by the same equation, and the height z is given by the same equation but shifted by L1. Once we have this distance r, we then further resolve it across x and y based on this angle theta 1 to get the x, y, z of the tip, and these are the final 3 equations. Okay, so why do we need matrices then? As we saw, different geometries of the arm have different ways of how they operate, and it gets tricky to derive separately for each geometry of the arm how its angles and positions vary to give the final result. Also, it is very difficult to organize these equations for more and more degrees of freedom, 4 degrees of freedom, 5, 6, 7 and so on. So to make things simple, to make the derivation more automatic, and also to better organize the equations more in a compressed way, and to make computers easily work with it, we use matrices. Okay, let's look at coordinate systems and frame changes. We already saw that when we computed the 2-link arm. We saw that we derived the end effectors or the end of the arms equation relative to the elbow's position first, and then we shifted it by the x1 and y1 coordinate. So to more formalize this, we have coordinate changes and frame changes. So what is a coordinate frame? A coordinate frame is a set of axes x, y, z typically. Different people can have their own reference. I can say my center is the center of the world, but you can say that your center is the center of the world, and if you give your coordinates relative to your center, I should be able to figure it out relative to me where it is. So this is how coordinate transformations work. So where are they used in robots? Typically we attach different coordinates to the different joints in a robot and also to the end effector. Here we have attached this xy coordinate to the first joint. Here we have another xy coordinate x1 y1 to this this joint, and another frame to the third joint, and so on. To convert a point from end effector frame to the world frame or the base of the arm, we find coordinate transformations and then multiply those to get the final transformation. Let's look at it in more detail. Okay, so let's look at how this works. So as we saw, a coordinate frame is a viewpoint for measuring positions. It is defined by an origin and a set of axes. Every position is relative to some frame. Let's draw a coordinate frame and place a point. So here we have a frame A and a point 2, 1.5 defined in this frame. The x value is 2 and the y value is 1.5. Now imagine two different coordinate frames in the same space. So here the point P has a fixed position in space. In frame A, the point P is given by x equal to 3.5 and y equal to 2.5. But the same point is given in B with different numbers 1.2 and 1.4. Same physical point but different numbers. The coordinates change because the viewpoint changed. So why does a robot need multiple frames? Each joint creates a new coordinate frame. Each joint and the end effector have their own frames. When a joint rotates, everything downstream the joint rotates along with it. Each frame is attached to its link and moves with it. If the end effector is at 0, 0 in its own frame, so since the end effector frame will be defined with this point as the origin, the end effector will be 0, 0 in its own frame. But where will it be relative to this frame, base frame? How do we convert coordinates from one frame to another? This is what coordinate transformations tells us, and this is precisely what we need to know to derive the forward kinematics of the arm. So there are two cases. Case 1 with only translation. Here the two frames share the same direction. The y directions both point up, the x directions both point to the right. But they are displaced by this vector t with some height and some distance to the right. And we call this vector t the translation vector. So for this coordinate transformation, if we know the coordinates of this point at relative to the frame B, we can also convert it to frame A simply by adding t to it, because any point relative to B will be shifted by the same distance t. When we look at A. Next we look at rotation. Now the points are not shifted. Both of these coordinates share the same origin, but these angles are not the same. They are rotated by an angle theta. So now to convert the point from coordinate B to the coordinate frame A, we have to use the rotation matrix with a given angle theta. We will unpack the rotation matrix in future slides in more detail. Now for now let's assume that r of theta is a matrix and we multiply that to the point to get the transformation. Now what if in a general case we have both rotation and translation? Here the coordinate frames are rotated but also translated by t. The angle of rotation is theta. Now the general transformation is given by rotation and translation. We multiply the rotation matrix, then add the translation vector. Rotate first, then translate. Now let's look at how to pack R and T into one matrix, because we find it tedious to do these two operations separately. So generally the rotation matrix R is a 3D matrix for 3-dimensional space, but to combine translation we convert the matrix into a 4-dimensional matrix called the homogeneous transformation matrix. So here we have the rotation matrix, which is a 3x3 matrix. Here we have the translation vector, which has 3 components, x, y and z, and at the end we have this row with 3 zeros and a 1. So this is a rotation matrix with the rotation in the z direction, and this is the general translation vector, and the bottom stays the same. With this we can do the transformation in the general case with both rotation and translation combined with a single matrix T, and we append each point at the end by 1 to make this work. So vectors with 3 points become vectors with 4 points, but the 4th point is always 1. This is called the homogeneous trick. Now let's look at how to chain transformations. What if we have 3 frames instead of 2 frames? So we have 2 translation vectors, T from A to B and T from B to C. Sorry, not translation vectors, homogeneous transformation matrices, which encode both rotation and translations. So to convert the point P from C to B, we multiply this matrix BC. So point at B is given by TBC times the point PC. Next, from converting B to A, we use PA equals TAB times PB. Combining these two equations, we get PA is this transformation, then this transformation, then this point. So TAB times TBC times PC. Now you might get the intuition that we can chain any number of transformations by multiplying them in the right order. So multiply matrices together left to right from base to the tip. So for the two-link arm example which we saw, we can use this to easily derive the forward kinematics. But we have to first figure out the transformation T01 and T12, and then we can directly multiply them. So how does it relate to the SO101 arm? So the SO101 6DO form have all these frames, the base frame, then all the joints, then the final tool frame, whose coordinates which we want to figure out relative to the base frame. So we have these different transformation matrices which we have to derive based on the geometry of the arm T01, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6 and 6 to tool. But once we have that, it's just a matter of multiplying all these matrices in the right order. This is forward kinematics. We simply multiply transformation matrices to get the tool position. So what does the final matrix tell us? So the final matrix has 2 components, the rotation part and the 3 translation part, 3 coordinates of the translation. So these 3 coordinates of the translation gives the position of the tool tip relative to the base frame in 3D space. The 3x3 submatrix gives the rotation of the tooltip relative to the base frame. So with one matrix we have the full 3D pose, the position and the orientation of the end effector or the tool. So let's look at the summary of the transformation matrices. A coordinate frame is just a set of axis and origin, a viewpoint for positions. Same point can have different coordinates in different frames. Robot arms use one frame per link attached at each joint. A transformation matrix T converts coordinates by multiplying PA equals T times PB. We can change matrices from the base to tool by multiplying the coordinate transformation matrices. And this is the essence of forward kinematics. The order of matrix multiplication is very important. Matrix multiplication is not commutative, that is, we cannot change its order. T1 times T2 is not the same as T2 times T1. So we have to be careful when multiplying the matrices. We saw what a rotation matrix is in some detail, but we didn't go in full detail. Let's look at how 3D rotation matrices work from first principles. So in 3D we have three important rotation matrices. Rotation around the x-axis by angle theta, y-axis by angle theta, and z-axis by angle theta. And these are the matrices. So for the z-axis, this third column will be 0, 0, 1, and this will be zeros. Similarly for the y-axis, we can see the center column is 0, 1, 0, and this is 0, 1, 0. And the x-axis, we see the first column is 1, 0, 0, and the first row is 1, 0, 0. And this is where the transformation happens. And here, this is where the transformation happens, and here it is like a crisscross. This is because if you see around z, if you rotate something around the z-axis, only the xy coordinates change, not the z coordinate. That's why all the action is in the top part of the matrix. Similarly, around x-axis, only y and z coordinates change. That's why the bottom two parts are like this. And similarly for the rotation around y, only x and z change. So the y is left alone. Okay, so let's look at how to derive these rotation matrices. First we'll look at a 2D rotation matrix derivation, and then we can extend it to 3D. So as we saw in the previous set of slides, to find the total coordinate transformation matrix, we need to derive the rotation matrices first. Okay, this is the same diagram which we saw before. Two coordinate frames rotated between them by an angle theta. Both frames share the same origin. No translation is present, just rotation. We place a point P somewhere in the plane. R is the distance from the origin to the point P. In the rotated frame, i.e. x dash y dash, the point P makes an angle alpha. So from the x-axis, the original x-axis, the point P makes an angle alpha plus theta, as this theta is added. Now we need to know, if we know P's coordinates in the x dash y dash frame, how do we find them in the xy frame? We will just use simple trigonometry again. So since this angle is alpha, with opposite by hypotenuse and adjacent by hypotenuse using the basic trigonometry rules. We can see that with this right angle triangle, x dash is r cos alpha and y dash is r sin alpha. Now to find the xy coordinates, we use this right angle triangle where the angle instead of alpha is theta plus alpha. So the x becomes r cos theta plus alpha and y is r sin theta plus alpha. So same right angle triangle trick with the angle being alpha plus theta. To find the relationship between the x frame and x dash frame, we need to use the angle addition identities of trigonometry. Just as a refresher, cos a plus b is cos a cos b minus sin a sin b. Sin a plus b is sin a cos b plus cos a sin b. So here a is alpha for us and b is theta for us. Based on this formulae, we can write out x as r cos alpha cos theta minus r sin alpha sin theta, and y we can write it as r cos alpha sin theta plus r sin alpha cos theta. But we already know that x dash and y dash are r cos alpha and r sin alpha respectively. Substituting those in this equation, we get x as x dash cos alpha minus y dash sin theta, x as x dash cos theta minus y dash sin theta, and y as x dash sin theta plus y dash cos theta. Now we just use the matrix form. The same equations can be written as xy equals this rotation matrix times x dash y dash. Using the rules of matrix multiplication, we can show that this equation and this equation are the same thing. So if you look at the matrix multiplication, we get x dash cos alpha minus y dash sin theta as x and x dash sin theta plus y cos theta as y, which is exactly what we saw in the previous slide. So we can write pxy as rotation matrix of theta times p of x dash y dash. So just a numerical example with theta as 30 degrees. Using trigonometry, we get these values for cos and sin thetas, and we know that if we assume that x dash and y dash are 2 and 1, we can compute x and y with this matrix multiplication, and we get these values. This is just a visualization. We can see that as the rotation angle varies, the rotation matrix of theta also varies, and the x y coordinates also vary. Okay, here we used just xy. How do we extend this 2D rotation to 3D? In xy, there is only one rotation possible across the z axis. In 3D, we can have three fundamental types of rotations about the z axis, the x axis and y axis. The SO101 arm uses these rotation matrices for various joints. The first one is across the z axis, next to across y, then across x, then across y, and then across x. We will see this in more detail later. So these are the three rotation matrices, where C of theta is cos theta and S of theta is sin theta. So the pattern is find which axis stays fixed, and that becomes an identity matrix. Then put the 2 cross 2 rotation matrix which we derived in the other entries. for Ry we need to flip the signs to make it adhere to the right hand rule. You can think about it in more detail on your own. So these are just some key properties of the rotation matrix. If you are interested, you can just go and read through them. So this is similar to the coordinate transformations which we saw previously. Here we just write the translation matrix and rotation matrix separately, just to showcase that we need rotation matrices for each of the joints. So the final transformation is given by translation, then rotation, then translation, then rotation, and so on. We have a rotation matrix for each of the joint angle. So let's look at a summary. Two frames are shared by an origin but rotated by an angle theta. Using trigonometry angle addition identities, we convert the frame from one frame to another. Then we see that it can be generalized to a 2D rotation matrix given by r of theta is cos theta minus sin theta and cos theta. Then we can extend it to 3D to get RZ, RX and RY rotation matrices. The SO101 OM uses ZYY, XYX rotations. We change these rotations and translations to get the forward kinematics. So let's take a look at the homogeneous transformation once again, just as a way to make you understand a bit better. So instead of representing the point as xyz, we add xyz1. We add 1 at the end to all points. So an homogeneous point is given by the original xyz with an 1 at the end. To get the homogeneous transformation matrix, we have the 3×3 rotation matrix at the top left side. Then we have the translation vector tx, ty, tz, and at the bottom we have this identity vector, 3 zeros and a 1. So this implements the equation r times the position, rotation matrix times the position, then an addition with these three values. So combining that entire thing into a single matrix. So this is seeing it in more detail. So the xyz point, appended it 1. If we multiply that homogeneous point with the homogeneous transformation matrix, we get these values. So the rotation matrix multiplied values, then these translation values. And at the fourth point, since this xyz is multiplied with 0 and this 1 is multiplied with 1, we always get a 1. So each time we use this homogeneous point, we always get an homogeneous point, so that everything stays consistent all the time. So we can change this multiple times. Okay, now let's look at the concrete example of how to implement these matrices for our OM. So we have these transformations for our OM. The shoulder pan is across z axis by theta 1, then shoulder lift is rotation across the y axis by theta 2, then theta t3 the elbow lift is about the y axis again, theta 4 elbow rotation about the x axis, theta 5 wrist flex about the y axis, theta 6 wrist roll about the x axis. So we have all these rotation matrices, and we also have the translations. The translations are given by the geometry of the arm. So we multiply all these to get the forward kinematics. So we use the transformation matrix method to derive the forward kinematics. So the strategy is, for each of the joint we compute the transformation matrix and multiply all those, chaining them together to get the final transformation matrix between the base and the tool. So as a refresher, we use these as the Lego blocks. So the rotation matrices around Z, X and Y, also called as pan, pitch and roll, are given by these, which we saw before. So when there is no translation, we use 0, 0, 0 as the translation vector, which represents no translation. And to independently represent a translation, we use an identity matrix for the rotation matrix, and we have the XYZ translation vector here. So to give the actual forward kinematics for the S101 6 degree of freedom arm, we have to use these exact geometry values based on the structure of the arm. We have A1, H1, A2, H2, L1, D1 and L2, L3, D2, L4 and L5. The L values are the link lengths and these are some of the offsets. So we have different values for each of these offsets, which you can look at in more detail by looking at the structure of the arm. So we compute the transform matrices step by step for each of the coordinate. So for the T01 shoulder pan, we have the rotation across the Z axis, which is given by this rotation matrix. We have a translation move forward in the X direction by A1 and upward movement in the Z direction by H1, which is given in the translation part. Then for the shoulder joint, we have a rotation around the Y axis by theta 2, and we have similar translations forward A2 and up H2 given by this matrix. Similarly, for the next transformation elbow roll, we have rotation around Y by theta 3. We have two translations, but this times in negative L1 and D1. Now for the joint which we specifically added for the 6 degree version of the arm, we have a rotation around the X axis and the translation by L2. Similarly, for the next rotation, wrist pitch, we have a rotation around Y by theta 5 given by this matrix and a translation plus L3 along X and plus D2 along Z. Here D2 is small, only 6 mm, but it's a real offset. Similarly, for the wrist pitch, we have another rotation matrix, this time around X, and a translation L4 in the X direction. The tool transformation, which is the final coordinate which we want to find out, has no rotation since it's just a static point, but it is shifted by L5. So once we have all these matrices, we can compute the total final chain as T01 times T12 times T23 and so on up to T12. So this gives us the grand result, the total transformation matrix. So as we saw before, the final transformation matrix encodes both position but also the rotation information. So to use the rotation information effectively, we can use something called the attack or approach vector. This gives us in which direction the end effector will point to when we pick up an item or move to some point. We can think of it like a flashlight. The approach vector tells you which direction the gripper is pointing, just like a beam direction of a flashlight. So if the approach vector is 1, 0, 0, the tool points forward. If it is 0, 1, 0, it points to the left or along the y-axis. If it is 0, 0, -1, it points downward along the negative z-axis. So these are some examples of the attack vector. So how do we implement it in code, or how do we convert this as an algorithm? So first let's look at the pseudo code. We start with the identity matrix. For each joint we build its transformation matrix based on the rotation of the joint angle across some axis and the geometry of the arm based on the link lengths. Then we multiply all of them together in the right order. Then with the final matrix, from the last column we derive the position of the end effector relative to the base, and with the top 3x3 matrix we derive the orientation. How does it look like in Python? So we have these different matrices for different transformations of different joints, and we start with the one identity matrix which is given by np.I. Then we multiply it, matrix multiplication is denoted as at, with the shoulder pan, then shoulder lift, then elbow transformation, elbow rotation transformation, wrist flex and wrist roll transformation, which is basically starting with an identity matrix, then keep on multiplying the transformation of each joint, finally the tool joint, to get the final matrix. And we just filter out the position and the orientation, i.e. the last column or the top 3x3 matrix, to get the orientation and position. If you know Python, this is pretty straightforward to understand. If you don't know, don't worry. So in this video we have looked at in detail how forward kinematics works from first principles, how coordinate transformations and rotations work, and how to change these transformations to derive the final transformation matrix. Here I didn't talk too much about the geometry of the SO101 arm. You can go back, look through how the arm structure is in more detail, and you can get a sense of why the exact A, H and L offsets come about. But the general principle is straightforward. For each coordinate we find the transformation matrix and chain them together and multiply them to get the final transformation matrix, and from that we derive the position and orientation of the end effector. Thank you.